a coil of wire in a magnetic field, it feels a certain torque. And that torque is related to the current that runs through the wire. If you put more current, you get more torque. It also relates to the magnetic field. If you have a stronger magnetic field, you get more torque out of that wire. Remember we had we derived the expression for torque at NIVA. If we also increase the number of turns, if I have more than one turn, 100 turns, 1,000 turns, 10,000 turns of wire, then that'll increase the amount of torque that I get out of that wire, out of that electric motor. But you have this funny thing that happens, and we mentioned this last time, I think, is what happens to the forces after this coil rotates 180 degrees. What happens to the forces? Because right now you have a force up on this side and a force down on this side. What happens when you flip this thing by 180 degrees? It switches, right? Because the current now, whereas the current was going into the page on this side, if I flip this, if I rotate this, then the current will now be coming out of the page on this side, because this side will come over here. So what that does is it changes the direction of the forces. So they are going like this, and then when it rotates, they're going to go like this. And actually, every time it rotates, the forces will change direction. And so you have to account for that, and there are a couple ways that we account for that. So as the loop rotates, the force changes direction. When the coil is rotated a full 180, so half a circle, the force is opposite what it was before. So in electric motors, you have to change the direction of the current. After each revolution to keep the loop rotating in one direction. Two ways to do this. You might be familiar with this. You can use a type of switch. These are kind of like the double pole double throw switch that you've used in lab. Remember you had that double pole double throw where it actually switches the direction of the current. Each time you go around, there will be some switch that will switch the direction of the current. In electric motors, these are called brushes. So you might have heard somebody there, rebuilding an electric motor, they have to replace the brushes. That's what those do, is they switch the direction of the current. And they're used in direct current motors. Now with direct current, if you make a plot of the current versus time, or if you make a plot, maybe more correctly is to say, if you make a plot of the voltage versus time, it doesn't really matter what you do. You'll get a plot that looks like this. It's direct. It's always constant. In contrast to this is DC. In contrast, if you make a plot of V versus T of what we call alternating current, AC, then this looks like this. It actually changes, goes from a positive value to a negative value, back and forth, at a prescribed frequency. And we'll have a chapter on this. We'll get into inductors and inductance and all that jazz and look at AC electricity. It sort of opens up a whole new math ballgame as we look at alternating current. So another way then to deal with this problem of having forces that change every half turn, and by the way, if you leave that electric motor without changing the current, all it's going to do is it's going to flip and flop, kind of like a fish, right? Flipping and flopping. And that's not very useful. It's hard to take that kind of motion and make it into something that you can use. It's easy to take a continuous rotational motion and convert it, have it go onto an axle, and then convert it into something that we can use. We can drive a vehicle or drive some sort of mechanical system. But it's hard to make that flip-flop motion useful. So another way to have this is to just use alternating current. Because in alternating current, the current already goes back and forth. It changes back and forth at a prescribed rate. And then in the United States, if you're using sort of the grid, that's about 60 hertz. But you can create circuits that will change that frequency if you need an alternating current at a different frequency. You chemists will probably get into this in instrumental. I think, as I said, Dr. Wayman's doing more circuits now. if you go into graduate school too, it depends what you're doing in graduate school, but you might see that more if you're building your own instruments. Okay. So let's look at generators. These are actually, let me show you a video first before we get into that. This is just a video of an electric generators. So if I have a current carrying wire in a magnetic field, it's going to experience a force. And in a similar way, if I exert a force onto a wire in a magnetic field, then that will it will experience a current. You can imagine if I have, charges in here within this wire right here, and I force them through this magnetic field, I have a positive charge with a velocity going through a magnetic field like that. We've already found that that experiences a force, and that force is going to cause it to move in the upward direction by our right-hand rule. We can calculate what that force is. And so in a similar way, when I force this through the magnetic field, it's going to feel a force upward in that direction, which is going to create a current through that wire. And so in this case, the direction of the current in the wire is going to be up, assuming that we have positive charges that are flowing. As I said, I have a positive charge moving with a velocity in this direction, and so it's going to experience a force in the upward direction. So a generator then works exactly the same as an electric motor. And I have a little hand crank generator that I brought today. I'll pass it around so you can see it, but it's really just an electric motor. Y'all seen electric motors like in little toy cars and stuff? That's an electric motor. You can buy them on the internet for $1 or $2. But there's a little electric motor. It's just wired up to a little light bulb, and then it has an axle that or a handle that attaches to the axle of the motor. And so if I take this and spin it, then I can generate an electric current. And that's how generators work. They just have a big coil of wire that sits inside of a magnetic field. You turn the coil of wire by some mechanism, whatever that mechanism is, and it generates a current. And this is my hand. But what are some other ways that we can turn the coil of wire in a magnetic field? Water power, so like hydroelectric power. So you just have water that spins through these turbines and causes them to spin. Wind power, right? So you can have a windmill that spins and does turns the light on. The most common way, though, of course, is what? Coal, right? Coal or gas. In Louisiana, we get a lot of our power from the nuclear Waterford 3 in New Orleans. And the way those work is they're just a heat source. Any heat source, right? It can be coal or natural gas or nuclear power. Any heat source. They use that to heat up water, and then that water produces steam, which turns these huge steam turbines. Do this. So all you have to do is take some motion that's spinning, and you can produce electricity, whether it be wind or nuclear or coal or however it is you'll produce that motion. There are other ways to produce electricity too, like for example, what's it called? Like tidal motions. They'll put these generators out in the ocean, and they move up and down, up and down. And there are ways, it's a little bit complicated and kind of difficult to get it to work well, but you can take that up and down motion and just so with this, I have two of them. Just to convince you that a generator is really just an electric motor. I can have this. Here, Frank, you hold those while I fast. So I have another one here. A generator is really just a motor in reverse. So what do you think will happen if I connect these? So I have a wire that comes out of one little hand crank generator. So if I spin this, it'll produce a current. And I have it set up so that the current will go into this other generator. What do you think will happen? I don't know. You think they'll both light up? Let's see. Frank, will you hold that? Sort of just hold it up so people can see it if you don't mind. So they do both light up, but did you notice the handle on this one? It's an electric motor, right? If I provide a current to the electric motor, then it's going to make the electric motor spin. An electric motor is just the opposite of a generator. It's just a generator in reverse, or a generator is a motor in reverse. I'll pass this around. They're kind of noisy, so don't get too carried away with it. But you can take a look at it, and even if you want to spin it sort of quietly a couple of times. I have another video I want to show you. It's about wind turbines. It's from Mass Spectrometer. You ever watch that show? On PBS? You ever watch it? I don't know if it's still on. It's a great show, though. They're just installing a wind turbine. Of course, the commercial wind turbines are much bigger, and they work by a similar method. But if these huge wings or whatever that are on the turbine, and they feed electricity into the grid, and it works very much in the same way as that. Of course, another way to produce electricity is by solar panels, and that works by a different process where the photons from the sun come in and they liberate electrons which move, and that creates current. And many of you chemists might actually work in areas like that because, well, it's a big deal now to create solar panels that are more efficient. And those are chemical processes. That's something that chemists need to work on and to do. Rebecca talked a little bit about that. All right, so let's also look at a mass spectrometer. We talked about this a little bit, but if I have a charge that's moving in a magnetic field, the force is perpendicular to the velocity. And if the force is perpendicular to the velocity, then the charged particle will move in a circular path. And we talked about this. It's the centripetal force last semester. Centripetal force is perpendicular to the velocity. As it is with magnetic forces, that they're always perpendicular to the velocity. So if the force is perpendicular to the velocity, how is it going to change the velocity? The velocity is a vector. It has a magnitude and direction. Is the magnitude of the velocity going to increase, decrease, or stay the same due to the magnetic force? It'll stay the same. That's what centripetal forces do. They don't change the magnitude of the velocity. They only change the direction. Right? We saw centripetal force is like a ball on a string. You spin it around. It doesn't change the velocity or the speed of the ball. It only changes the direction of the velocity. And so magnetic forces are similar. As a result, they don't change the energy of a particle. Only the direction. When I say they, I mean the magnetic forces. So F, I'll call it F sub B. The magnetic force, because it's centripetal force, doesn't change the energy of a particle. It only changes the direction of the velocity. So for example here, if I have a positive particle, it's going to feel a force that is upward. It'll follow a path that looks like that. It's going to feel an upward force. Remember, if I have a negative particle, then it's going to feel a downward force. If my velocity is in this direction, then my force will be the opposite of what a positive particle would feel. If theta is 90 degrees, as it is in this case, because my velocity and my magnetic field are perpendicular to one another, the sine of 90. Is that a dog? It's Guido. That Guido. Y'all know Guido? The president's dog? That little, it's like a French papillon or something. French for pillow, I think. Alright. Is that butterfly? Okay, well, it's not papillon, it's something else. The president what? With the dog. Really?
But he meant like Donald Trump, the president.
No, President Murphy. No, I don't know if he has a dog.
He doesn't. He's
Are you serious? We saw the one Bo. Ever tell y'all this? He was peeing on the front lawn with the secret. He had like 3 Secret Service guys with him. I guess they were Secret Service. They were in like black suits. We were starstruck. All right. Anyway, so F is QVB. And since our force is a centripetal force, remember our centripetal force is mv squared over r. The centripetal force is the mass times the centripetal acceleration, which is v squared over r. That's from last semester. I don't remember the chapter. But if we solve this for r, it gives us the cyclotron equation. And this is on your equation sheet, so don't bother memorizing it. But if I solve it for r, then I get r is mv over qb. And so a mass spectrometer uses this principle. The one that we have upstairs uses this principle to find the mass to charge ratio of particles. So I solve this for the mass to charge ratio. When I have an unknown particle, I don't know either its mass or its charge, but if I can find the ratio of its mass to charge, then I can go a long ways towards identifying that unknown particle. And all I have to do is give the particle a certain velocity, which I can do. We'll accelerate the particle in an electric field to give it a certain velocity. And then I determine that I set the magnetic field, and then I measure the radius of the path. And when you do that, you can figure out the mass to charge ratio. So say, for example, I give a particle a certain speed, say 1.79 million meters per second. I make it go into a magnetic field, and then I measure that it has a path of this radius of 0.16 meters, 16 centimeters. It's sort of an upper-level undergraduate experiment. You chemists probably won't do it, but you can take these coils of wire. They're about this big. It's usually sort of physics majors that do this, but I don't know. Don't you might have PChem? I might say PChem out here. Might see it PChem. You take some coils of wire like this, and you run a beam of electrons through it, and then you can figure out what is the mass to charge ratio of the electron. That's how they first determined the mass to charge ratio of electrons back in the early 1900s. Is they had these coils of wire to create a magnetic field, and then they run a beam of electrons through it. So here, if I wanted to find this particle, I would determine its mass to charge ratio. That's RB over V. R is 0.16 meters. B is 0.35 Tesla. And V is 1.79 times 10 to the 6 meters per second. And then that'll give me the mass to charge ratio. See, that works out to be 3.13 times 10 to the 8th, minus 8 rather. And so, you have some idea of what the particle is. So you go and you look, and you say, what are the mass to charge ratios of the possible particles it could be? And you would pick out tritium here, because it has a mass to charge ratio of 3.13 times 10 to the minus 8 kilograms per coulomb. And so you determine that that particle has to be tritium. All right, you ever used the mass spectrometer upstairs? Or have you used it yet? No? Use it in quant, okay. Do you use it in a similar way? What do you determine when you use the mass spectrometer? Oh, okay. What does it report to you? Does it just spit out what the particle is, or?
Yep, it goes to the library and suggests various
Oh, okay. Well, this is what it's doing, and it's measuring that radius and calculating the velocity and measuring the mass to charge ratio. You can build one. It's not that hard. You just need copper wire, vacuum tube, some electrons. You're good to go. All right, let's try this quick test. You'll probably have this on your next exam, so let's just practice. This is a similar question. Just identify the particle here. solving for M over Q, with the ratio, and take out the right one. All right, just a few more seconds. I'll stop at say 225. 225. That looks like everybody. 225. Just a few more seconds. Okay, good. Easy peasy, right? Yeah, so you just say, what is it? R is, or M over Q is RB over V. You have the values for that. What does it come out to be, the mass to charge ratio? 1.04 times 10 to the minus 8. So you can probably just determine that this is the one, the 1.67 over 1.6. It's the closest one to 1.04. So you can just stop there and say it has to be hydrogen. All right. Hey, why did the stadium get hot after the game? All the fans left. Okay, let's see. Another video I want to show you, I think, sort of how a mass spec works.
The electric motor is
Magnetic fields are vectors, so they can add up. So in this case, what is the direction of the magnetic field at point A? And what you need to do is you need to determine the direction of the current for each of the individual wires, and then I want to know how those vectors add up. There are really only a couple options. They can be into the page, out of the page, or you could have no magnetic field. Because you know that these things aren't going to produce a magnetic field to the left or right, that it's going to be going around that wire. So you need to figure out the magnetic field due to the two currents, and what is the sum of those vectors. And we will wrap up with that. I'm going to return your exams. I posted the solution this morning. All right, let's stop at 1:15. 1:15. It's 5 more seconds. Okay, let's see. Due to this wire, it's into the page, out of the page, right? Using my right-hand rule. And then this wire, it's into the page, out of the page. So here, my magnetic field is going to be out of the page. Those two vectors will add up. So B is the right answer. It's out of the page. All right, let me tell you a joke anyway. This is a good joke. I've been saving it for you. You ready? So it's really sort of more of a question. If you're American when you go into the bathroom, and American when you come out of the bathroom, what are you when you're in the bathroom? European. Okay, let's see. Exam was pretty good, although I understand if you didn't do as well as you'd like.